Hello, Professor Balaji. Our topic is convolution neural networks. This is my team, Manish, Anoop, and Pratishruti.
Convolution neural networks, or CNNs, are a category of neural networks that have been proven effective in areas such as image recognition and classification. Before we see our code and the output, let us understand what convolution neural network is using an example of classifying X and O's. So when we are classifying images as X and O's, we need to take care of scaling, rotation, weight, and translation in order to fit or map it to either X or O. Deciding is hard because when I feed it to the computer, this is what a computer sees, and it finds that these are the areas which are of a mismatch, and it says that these two images, even though they're similar, it says it's not equal. So what convolution neural network does is it's going to break down the image into features. For example, it's broken down this into 3 features, and it's then comparing the features to the image. So this is the math behind convolution. It's taking the feature and it's multiplying across the entire matrix. So when there is an exact match, it's 1. Then later I am taking the average of the window. So that's 1, and that 1 is stored here. And we do the same thing for the entire image, and this is the map that we get. Well, I use another feature and do the same thing. These are the maps which I get. And this becomes my convolution layer. And next we do pooling. Pooling is generally done to reduce the size of the image. We're using maximum pooling here. As you can see, it's going to stride the window here and it's going to take the maximum of this particular value. And this is done across all the convoluted image set. The next one is normalization. Since we have negative values and these have no impact on our convoluted layers, we just replace them with zeros. And this is our entire stack of images what we have. Perform this operation multiple times in order to get smaller and smaller image. For example, in this case, we've run it twice to get a smaller stack of images here. We then stack these maps into a single array and then pass it to a neural network. And after our neural network is trained, we will be there'll be weights which will be assigned to each of them, and when I give an input, it's going to vote whether it's an X or an O, and then based on the highest probability, it's going to classify whether it's an X or an O.
These are the few concepts that will help us understand convolution neural networks better. The first one is convolution. Convolution is a pointwise integration of two functions. The second one is backpropagation. The goal of backpropagation is to optimize the weights so that the neural networks can learn how to correctly map any arbitrary input to output. The third one is window size. The size of the image on which convolution is performed is called the window size. Window stride. It is a shift of the window size across the input image. Whenever we do not define a window stride, the default value is 1. Next one is an activation function. Activation function is generally a sigmoid or rectified linear unit. Rectified linear unit is used because it has got better experimental results. These two functions are helpful in varying the input between 0 and 1 gradually. The next one is dropout. Dropout is a fraction of input units which are to be set to 0 to help the model from overfitting. Next one is flatten. Flatten converts a multidimensional array into a single dimensional array. The next one is dense. Dense is the dimensionality of outer space for a particular layer. It basically gives the output nodes for a layer. Specifically for the last layer, that's the fully convoluted layer, the dense value will be 1. Pooling. Pooling can be two types, minimum pooling or max pooling. Minimum pooling selects the minimum value in the particular region, Max pooling selects the maximum value in the particular region. Both of these things help in reducing the size of the input. Next one is the batch size. Batch is a set of n samples. The samples in a batch are all processed independently and in parallel. The larger the batch, the better its approximation. Next one, epoch. Epoch is generally defined as one pass over the entire data set. It is basically used to separate the training into distinct phases.
The concepts which we used previously for processing X and O's, the same concepts we will be using now to process a more complex data set which consists of cats and dogs. We are using Keras library and we are using TensorFlow as the backend, and we have named it as K. So in this data set, we have cats and dogs, which we have divided into two different directories, and each of the directory consists of 2000 cats images and another directory with 2000 dogs images for training, and 800 cats images and 800 dogs images for validation. So we are training this model with 50 epochs, and batch size is equal to 16. So here we are mentioning the input shape of the images. If we do not mention it as channels first, it will automatically take the input shape as image width, image height, and 3 as the parameters. We are using a sequential model because sequential model means we are using a stack of layers, and here in convolution 2D we are using 32 filters, and it has a stride of 3 cross 3. So if the stride is not equal to 1, then it is an invalid stride. Here we have used activation function as a ReLU and the max pooling and we are creating a max pool of 2D images which has a pool size of 2 cross 2. Here, as we can see, there are 3 hidden layers. So we are training this model with 3 hidden layers, and here we are compiling it for the loss as binary cross entropy. So the loss will be the sum of all the losses in each of the layers, and we are calculating the metrics because we are calculating the accuracy of this model. And now we are training the data set by rescaling and flipping the images so that the training can be done properly. And here in the train generator, it is taking the here the training directory as a parameter so that each of the images can be processed and trained. And here we are using the image width and height as 150 cross 150, and it will have a binary output. So here again we are using the validation generator to validate the data, and we are fitting this this model in this. We are showing NB we are assigning steps per epoch is equal to NB train samples, that is the batch size, and we are and here we have saved the model and the weights in final.h5 for testing.
We have already seen that our training model has an accuracy of 81%. Now let's run this particular model through a set of test images. So to begin with that, so we are loading our training model, and then we are passing 50 images of cats and dogs. And what we're doing here is trying to predict whether it's a cat or a dog. And after it predicts as a cat or a dog, we need that to be saved in a folder based on whether it's a cat or a dog here. So as you can see, the folder is currently empty, and now let me run the code. Now it has completed running, and as you can see, it has already predicted for the 50 images that we've got. Let's look at the folder. Now, if I get into the cats folder, I have 21 items that it has classified as cats, and as some of you can see that there are some images of dogs that it has misclassified as cats. So it has misclassified 3 of the images out of the 21, and in my docs folder there are 29 items. So amongst the 29 items, it has misclassified 8 of these. So it has misclassified 8 images of dogs as cats. So in total, my misclassification rate is 0.22 because it has misclassified 11 images of cats and dogs wrongly. So our training model had an accuracy of 81%, and our test case has an accuracy of 78%.